Hey everyone, and welcome. You ever just look at your phone and wonder, how does all this magic actually work? Well, today we're going to pull back the curtain on one simple, absolutely brilliant trick that makes it all possible. Okay, let's just dive right in.
Seriously? Think about it. The phone in your pocket right now is way more powerful than the computers that took people to the moon. So how do they pack all of that power into something so tiny? Well, the answer is probably not what you're thinking.
Yep, that's it. The big secret to handling all that insane complexity is to focus relentlessly on making things simple. I know, it sounds like a total contradiction, but just stick with me here, and you'll see how this one single idea powers our entire digital world. Okay, so first things first. To get this, you need to understand the massive problem we're up against. All our gadgets are just full of these tiny, tiny little switches. And I'm not talking a few. Just imagine trying to drive through a city with a billion streets and no map. A complete mess, right? It would be pure chaos. That's kind of what the inside of a computer chip could be like. So, engineers need a way to turn that tangled mess into a super efficient highway. They have to simplify the logic. And this is exactly why it matters so much. When you simplify a circuit's design, you use fewer parts. And fewer parts means it's cheaper to make, it's physically smaller, and it runs much, much faster. This is the secret sauce, you know? It's what makes technology better and more affordable for all of us. So to build that super efficient highway, we need a special language, a language our computers can actually understand. But don't worry, it's not some crazy complex mathematical monster. It's actually a language based on just two very simple ideas, on and off. This language has a fancy name, Boolean algebra. Now, please, don't let the word algebra scare you off. It's really just a bunch of common sense rules for dealing with ons and offs, or as computers see them, ones and zeros. Let me just show you a couple of these rules and you'll see how simple it really is. All right, here's a rule. In Boolean logic, that dot just means and. So this is saying x and 0 always equals 0. Okay, that sounds a little abstract, right? So let's make it real. See, if you have a light bulb and it's wired to a switch that is permanently glued in the off position, it doesn't matter what else you do, that light is never, ever turning on. X and off is always off. It just makes perfect sense. Let's do one more. Here, the plus sign means or. So the rule says x or 1 equals 1. Again, sounds a bit like math class, so let's connect it to something we can actually see in our heads. So imagine that same light bulb is now hooked up to a power source that is always on. It doesn't matter what any other switch is doing, does it? That light is going to be on, no matter what. X or on is always on. Simple, powerful, common sense logic. So using these simple rules, engineers could take these long, really complicated logical expressions and just shrink them down. Let's quickly walk through how they used to do it the old-fashioned way, step by step. So look at this. We start with this long thing. But by finding what's common and applying those simple Boolean rules we just talked about, we shrink it down, step by step. Each step makes it shorter, more efficient. That means fewer switches, less cost, more speed. But, man, this looks like a lot of work. There has to be an easier way, right? Well, what if I told you there is a much smarter, way faster, and honestly, a lot more fun way to do the exact same thing? Okay, this is where the real magic happens. So forget all that text and algebra for a second. Look at this. This is a Karnaugh map, or what everyone calls a K-map. It's a visual tool that does the exact same job of simplifying logic, but it turns the whole thing into a kind of cool visual puzzle. Yeah, a K-map is basically a special way of drawing out all the possible outcomes on a grid. It lets our brains, which are great at finding patterns, just see the simplified answer almost instantly, instead of grinding through all that algebra. It's a brilliant, brilliant shortcut. And the process itself is just so elegant. You take your logic problem, and you just fill in the boxes for the on states, the ones on this grid. Then you just play a game of connect the dots. You look for the biggest possible blocks of ones you can draw. Each big block you circle is one piece of your final super simple answer. It's that easy. But, real life is messy. Engineering is messy. Sometimes you have situations or combinations that are just impossible. They'll never happen. Or maybe for some inputs, we just don't care what the result is. What do we do then? We use this fantastic little trick called a don't care condition. We mark it with an X. Think of it like a joker in a deck of cards. It's a wild card. You can use an X to count as a 1
if it helps you make an even bigger group. And if it doesn't help, you just ignore it. This gives engineers even more power to make their circuits as lean and efficient as possible. Okay, so we've looked at the rules, the algebra, the cool visual grids, but where does all this stuff actually show up in our world? Let's bring it all back to the gadgets you use every single day. Literally every single one of these things exists because of this principle. The reason your phone is so incredibly powerful is because millions of engineers used these very techniques to simplify billions of switches inside it. This logic runs everything from the traffic lights that keep our cities from jamming up to the life-saving machines in hospitals. This isn't just some textbook theory, it's the actual foundation of our modern world.
And this image just says it all, doesn't it? From these simple rules, from a simple grid that looks like a puzzle, we can build systems that are almost impossibly complex. It's just amazing. It really shows you the power of finding that one simple path through a very complicated problem.
It really makes you wonder, right? I mean, if this simple language of on and off has already taken us from computers the size of a room to supercomputers that fit in our hands, what is the next generation of creators and engineers going to build with it? What comes next?